You may recall from yesterday that we, in preparation for the two-phase method, we said what if the origin is not inside the feasible region, and we introduced a new constraint. X1 had to be greater than 3x2 plus 2. And that's how we fell into a minus x5. We added an artificial variable and we got going. Now, what happens if we want to apply the dual simplex method? So let's see if we can apply the dual simplex method here. What we did is we added, we saw this problem. How do we find an initial basic feasible solution? Well, what the way we could make use of the dual simplex method is by first recalling first. We did solve. We solved maximize x1 plus 2x2. X1 plus 3x2 is less than or equal to 16, and x1 plus x2 is less than or equal to 7. And the way we solve this is at the end we had the equations that x2 is equal to 9/2 and minus a half x3 plus a half x4, and that x1 is equal to 5/2 plus a half x3 minus 3/2 x4. And then z, I'm going to leave a little bit of room. Z is equal to 23/2, which is 11.5, minus a half x3 minus a half x4. Now we have a new constraint. That x1 minus 3x2 had to be greater than 2. Moment back. X1 had to be greater than 3x2 plus 2. Let's start from there. X1 had to be greater than 3x2 plus 2. And so therefore we have x1 minus 3x2 is greater than or equal to 2, and then we add a surplus variable, which is x1 minus 3x2 minus x5 is equal to 2. Now, since x1 and x2, x3 and x1 and x2 are basic, we really have a new equation that says that x5 is equal to minus 2 plus x1 minus 3x2. Correct? And we want to add in here, we want to add a new constraint, then take over from there. So we're willing to accept an initial solution which is not feasible. It is optimal right now. As you can see here, the minus a half is there and minus a half is there. So we are optimal, but we want to introduce something. So now, since x1 and x2 are basic, we have to replace, we have to substitute. So x5 is equal to minus 2 plus 5/2 plus a half x3 minus 3/2 x4, and then that takes care of x1, and then minus 3, and then we have x2, which is 9/2 minus a half x3 plus a half x4. And so now let's see what we got. we got minus 2 plus 5 halves, so we're dealing with halves, so that's minus 4 halves plus 5 halves is plus 1 half. Plus 1 half, we got minus 27, so that minus 26 halves, which is minus 13. And then we're dealing with x3. We have plus a half, plus 3 halves, so that's plus 2x3, so a half, and 1.5, that is 2x3, and x4 is minus 3 halves minus 3 halves, so that's minus 3x4. Okay, so now we have a new equation which we are going to then insert in here. So x5 is equal to minus 13 plus 2x3 minus 3x4. That's going to be inserted here. And once it's inserted, then we can carry on. So now let's we can erase the factor new constraint because we have entered it. Okay, and now the way we work it is let's eliminate this as well, and let's look at this. It is optimal, but it's not feasible. So that's what we were talking about before. So now the question is, if we're trying to remove this infeasibility. This infeasibility can only be removed by increasing x3. By increasing x3, we can overcome this infeasibility. But we want to do it so at this point what we'll have is that x3 enters and x5 departs, and you'll see that everything will remain. This will remain with because x3, as you will see, will have a plus x5 element in there. So let's follow up on this. So we change the roles of x3. This is the pivoting equation. Let's just take a pause. Okay, so we have x5, which is clearly infeasible, and we want to remove this infeasibility. To remove this infeasibility, sometimes you can have more than one variable infeasible. In this case, we only have one. So x5 departs. So the dual simplex, we first decide on the departing variable. Okay, so the depart x5. And the question is the entering variable. The entering variable has to be maintained such that these coefficients of x3 and the coefficients in the z equation remain negative. That means we remain optimal. Okay, so super optimal. This is what we were talking about. So right now we've inserted this, and it turns out that you pick the coefficients which are positive. So you ignore this one, you pick the positive. So entering variable, we take the lowest, and although the argument for as this increases and that decreases, which was the argument for the departing variable in the simplex, was more straightforward. The argument this is a little bit more complicated, so we just take, I'll tell you what it is. It's the smallest c over a. So and where a is positive. Okay, so we take a half over 2, but there's nothing else to compare it to. So this time x3 enters, and after this problem we'll do another one where we do have a choice, and we will apply this lowest c over a argument more effectively. So what we have is we need to identify the x5, x3, this is the pivoting equation, and so we take we need to know what x3 is. X3 is equal to, so we divide by 2, 1/2, so it's going to be 13 over 2 plus 3 over 2 x4 plus 1/2 x5, and then that has to be substituted in x2 and x1. So x2 is going to be 9/2 minus 1/2 x3, and that's where we substitute this. Which means that x2 will be equal to, it'll be 18 minus 13, that's 5/2. And then we have minus 3/4 plus 1/2, that's minus 1. Be careful here. Minus 3/4 plus 2/4 is minus 1/4 x4 minus 1/4 x5, and then this can go, and then we have x1 is equal to 5/2 plus 1/2 x3, and that's where we substitute. Minus 3/2 x4, and this is equal to x1 equals to so 10, that's 26/4, that's 13/2. Sorry. So 10, that's 23/4. Minus so we have plus 3/4 minus 6/4 is minus 3/4. It's minus 1/2 x4 plus 1/4 x5. Finally, we have z is equal to 23/2 minus 1/2 x3 don't know if there's enough room here. So that's 46, that's 47/4. Minus x4, minus 3/4 minus 1/4, and minus a quarter x5. So this is optimal, and now we're feasible. We should have been able to see right away that we are feasible. We have x1 equals 23 quarters, x2 equals to 5 halves, and we have a new objective function of 46 quarters. So this is how the dual simplex plays itself out. We'll do one more example with another one which we have encountered before, and we'll solve that with dual simplex, and then we'll be done with dual simplex.